This is Dr. Sridhar. Back to you with another video session on electrical analysis parameters. And suppose if the mechanical system is known to us, if we want to convert that mechanical system into electrical equivalent system, then we have to find analogous parameters of mechanical elements in electrical engineering fields. So here in this video session, I am going to present electrical analogous of mechanical systems. Now, depending on the applied inputs, there are two types of electrical analogous that is nothing but force voltage and force current analogous systems. So suppose let me take a basic mechanical system. The basic mechanical system is nothing but it consists of one mass element and one dash part, and next one is one more element which is nothing but spring. So there are three basic elements are there, and here basically we can see a mass unit. The mass unit, if we are keeping on a fixed surface or rough surface, now with respect to that rough surface, the mass unit will provide or that will develop some frictional forces. And one more basic property of the mass unit is nothing but sometimes it may have some elasticity nature. So the elasticity nature can be represented as can be represented equivalent to a spring constant, and frictional force can be represented by using a dash part. So this is the first figure is nothing but it is the mechanical system. That mechanical system is having some mass unit and another two elements which are nothing but one dash part and one more spring constant. So the connection of these are like this. On this mechanical system, if you are applying the force, that force is nothing but input. If the input is applied on the given mechanical system, the mechanical system is shown here, and whenever you are applying a force in the same direction of applied force, there will be a response. That response is nothing but output of the system. What is the output of mechanical system? Now, if you are assuming that this system is a translational system, translational mechanical system, then the output will be a linear displacement. That linear displacement is also shown here, that is x of t. So it may be x or x of t. X of t is nothing but if it is a time dependent, that is more specifically we can represent the output or displacement as x of t. Otherwise, we can write x. So whenever you are applying a force, means if you are pulling that mass unit in the downward direction, in the same direction, the total mass may be displaced. So that is nothing but we can find some displacement at mass unit. Well, how many units? By x of t units. So force and x of t is clearly represented in the presentation. So f of t is nothing but that is the input force, x of t is nothing but that is the output force. This is about the mechanical system. Now second one is coming back to the electrical system. Now in the electrical system, basically there are three basic elements are there, just like in the mechanical system. Now what are the basic elements in the electrical system? Those are nothing but the passive elements. One is the resistor, inductor and the capacitor. Now if these three are excited with some inputs. So in the mechanical system, if you could see the input used for the excitation of the mechanical system is nothing but the force. Now here also, what type of input elements or input energies are there in the electrical system? Either it may be a voltage source or it may be a current source. These two are nothing but active elements. Now here, first let me take if a suitable voltage, if it is applied to the series connection of RLC parameters. Now RLC, these three are seriously connected with respect to the source. Now here in this electrical system, input I have taken as the voltage source. And what is the output means? Output means we can see some current in the system. That I is nothing but this may be the output here. So RLs, if you want to measure the voltage across the capacitor, that might be the output. Okay. Here more specifically what is the input and what is the output means? What is the excitation, what is the response? Excitation in the electrical system is voltage. Response is nothing but the current. If there is no voltage, we cannot see any current in the electrical circuits. So this voltage and currents can be treated as excitation and the response, or cause and the response, like that. So voltage, I am assuming as the input voltage, input source or input energy for the electrical system, just as the f of t, which is force in the mechanical system. And here the displacement is nothing but output in the mechanical system x of t. In the electrical system, I am assuming the current as the output. So output is nothing but that is the response because of voltage source. That is the intention of that. Okay. Now for this mechanical system, already we have studied so many times what is the differential equation. So which differential equation describes well the given mechanical system means m into d square x by dt square plus b into dx by dt plus k into x is nothing but the applied force. So what is the formula we have used in order to derive this second order differential equation, which is nothing but the mathematical equivalent of the given mechanical system, that is Newton's second law of motion. With the help of that fundamental laws available in the mechanical field, which is nothing but the Newton's second law of motion, we have utilized that law in order to derive the mathematical equivalent of given mechanical system. So the mathematical equivalent of given mechanical system is m into d square x by dt square plus b into dx by dt plus k into x is nothing but the applied force. So that is the law itself, that is summation over f. So net resultant forces acting at any point is nothing but the 0. So we may develop the free body diagram for the mass unit, and we can mark the input forces and the opposing forces on one side of the mass unit. So finally, by applying the Newton's second law, we can determine a force balance equation. So from the force balance equation, we can directly derive the second order differential equation, which describes well the mechanical system. So which mechanical system? Translational mechanical system. That is about this. So finally, the mathematical equivalent of the mechanical system is clearly it was given as this one. Now this is about the mechanical, and just come back to the electrical system. Here in the electrical system, one voltage source RLC. So let us use the Kicha Voltage Law. That is also Kicha Voltage Law is also fundamental law. We can make use that fundamental law in the electrical engineering field to derive the mathematical equivalent of given electrical fields or electrical loops. So here in this one, there is only one loop is there. In the mechanical system, only one mass unit is there. So here in the electrical system, RLC and the voltage, for this simple loop, if you are applying voltage balance equation with the help of Kicha Voltage Law, so V of t is nothing but R into I plus L into di by dt plus 1 by c integration over I of t into dt. This is about the mathematical equivalent of given electrical system. Right. Now, if you are comparing, because what is our intention here? Force equivalent to voltage. If we are assuming force is nothing but the voltage, or force is equivalent to the voltage, then whatever the equivalent of mass in the electrical, whatever the equivalent of dashpot in the electrical, whatever the equivalent of the spring in the electrical, that is our intention. So how can we do this? How can we make a comparison between the mechanical parameter or and the electrical parameters? Means, first of all, if we could develop the mathematical equivalent of two systems are equal, or if these two can be comparable, then up to some extent we can develop the electrical analogies of the mechanical parameters in the electrical systems. Now here in this video session, I am making that attempt to develop the electrical analogies between mechanical and electrical systems. Here, now R into I of t plus L into di of t by dt plus 1 by c integration over I of t into dt is equal to V of t. So what is this? This is the mathematical equivalent or mathematical model of given electrical system. What is that system here? RLC in series with the voltage. Now, is these two mathematicals, that is nothing but the mechanical equivalent differential equation and electrical equivalent differential equation can be comparable? No, because the mechanical equivalent differential equation is nothing but it is a second order differential equation, whereas the electrical equivalent is having first order differential equation, and again in addition to that we have some integrator term also. So let us, if you could eliminate that integrator by substituting the equivalent of this I of t in this electrical mathematical expression, then somehow we could succeed in deriving the second order differential equation. So let me do that. So what I am doing is, let us substitute the equivalent of I of t. What is this I of t? We know that the rate of change of charge is nothing but the current. So here I of t I am substituting dq of t by dt. What is this q here? Q is nothing but it is a charge. So let us substitute this I of t is equal to dq of t by dt in the electrical expression. Then what happens here? This is R into dq of t by dt plus L into d by dt of, next again dq of t by dt plus 1 by c integration over I of t is nothing but dq of t by dt into dt is equal to v of t. So this is the expression we can get if in place of I of t if you are writing dq of t by dt. Then what happens? This second term is L into d square q of t by dt square. This is nothing but I am writing here. Next one is R into dq of t by dt. So I am writing here plus R into dq of t by dt plus last term is 1 by c integration over d by dt. So integration and d by dt gets cancelled. Remaining one is 1 by c into q of t, and this dt also gets cancelled, and this d and this integrator gets cancelled. So finally 1 by c into q of t is nothing but, so here this would be v of t. So 1 by c q of t is equal to v of t. So this is the mathematical equivalent of the given electrical system. So this equation and this mechanical equation, if you could keenly observe here, this electrical expression also, this is electrical equivalent is also a second order differential equation, and the mechanical equivalent is also a second order differential equation. So if you are assuming, now on the right side of this mechanical expression f of t is there, and on the right side of this electrical expression v of t is there. So this is the v of t. Now if the right side parameters are same, then what happens? The left side expressions will also same. So that is nothing but your d square by dt square, the coefficient of d square by dt square term in the electrical is L and in the mechanical is M. So if F is tending to voltage or F is equivalent to voltage, if you are assuming, then your mass will becomes inductance in the electrical system. And next one is second term, first order differential term, if you could compare d by dt. So the coefficient of d by dt in the electrical is nothing but the R. So in the mechanical that is nothing but the B. So this B damping dashpot equivalent is nothing but this is equivalent to R, and here this is L. And last one is, if you could compare this last term, simple term 1 by c into q of t, here k into x of t. So what is this here? Now k becomes reciprocal of the capacitance, and this holds good if x of t is assumed to be the charge. If the charge is assumed to be equivalent to the displacement, means if the charge is the output in the electrical system, then that will be the equivalent of the displacement in the mechanical system, which is nothing but the displacement, that is x of t. So these are, if force is assumed and equivalent to the applied voltage in the electrical system, then the mechanical mass is equivalent to the electrical inductance, and the mechanical dashpot is equivalent to the electrical resistance, and the mechanical spring constant is equal to the reciprocal to the capacitance, and the mechanical displacement, which is the output of the mechanical system, is equivalent to the output of the electrical system, that is nothing but the charge. So these are like this. Now we achieved this by equating or by comparing the mathematical equivalent of mechanical and electrical system. And one more important thing in this one, in the force voltage analogy, if we are assuming force is equivalent to the voltage, now these are the set of parameters equivalent to each other we can achieve by comparing the mathematical equivalent of that. In addition to that, so some of the other parameters also, now I want to calculate what about the I of t. So what is this I of t? I of t is nothing but on this expression, on this x of t is equal to q of t, if you are taking the differentiation with this, so dq of t by dt is nothing but the current. So on the left side, dx of t by dt is nothing but that is the velocity. Here, be careful with, generally velocity is also represented with v. Sometimes voltage is also represented with v. So that is some small sensitively you have to observe which one is velocity, which one is voltage. So these are the set of analogous parameter we can develop by comparing the equivalent second order differential equations of mechanical and the electrical. And one more thing, this is the set of analogous parameters if voltage is equivalent to applied force on the mechanical system. Now, this is some simple table we can prepare with the concluding remarks from the previous description. That is input, which is the independent variable. Normally, input is always independent variable. It never depends on any other parameters. So, we have chosen that input in order to reach the response. Or I want to see I have something in my mind that is nothing but the desired output. So, in order to reach the desired output, so I have chosen one input which is independent in the nature. So, that's why that made me to write here input is independent variable. So, that input independent variable in the mechanical system is force, and in the electrical system that is the voltage E, or sometimes we can write capital V of T or some V of T is also no problem. And output is always it depends, because this is the response of the input or response of the system with respect to applied input. So, output is always a dependent variable. So, what is that output here? Now, if the charge is the output in the electrical system, this is equivalent to what? Displacement in the mechanical system. Now, just now also we have discussed, if the displacement differentiation if you are taking, so velocity, then this velocity will be equivalent to the current. So, this is the one set of output parameters in the mechanical and electrical systems. And similarly, dissipative element, which is nothing but the dashpot, frictional coefficient, and so this is nothing but equivalent to the resistance R. And next one is the storage elements. So, mass will also store some energy, because we know that the mass will store some kinetic energy in it. So, that's made me to write here. So, mass is a example for the storage elements in the mechanical system. Similarly, in the electrical system, that becomes L. So, mass is equivalent to the inductance L. And one more storage element, that is nothing but the stiffness of the spring. So, spring is also stores some of the electrical mechanical energy. So, that made me to write this spring under storage elements. So, the equivalent of this spring in the electrical system is nothing but the inverse of capacitance, that is 1 by C. So, all these comparisons just now also we made just 1 minute before in today's video session only. So, from the concluding remarks, I have prepared a table. That table well describes the analogy between the electrical and the mechanical system, and provided that if the force is equivalent to be applied voltage in the electrical system. And what are the laws we have made here? Made to derive the analogous parameter between the electrical and the mechanical system means Newton's second law or Newton's laws in the mechanical system, and Kicha Voltage Law in the electrical system. And the level, suppose if you want to change the levels, and lever can be used in the mechanical system. So, gear system, if you want to change, now with the help of levers, we can change the potential, means strength from one level to the another level. So, which is nothing but equivalent to a transformer. In the transformer also what happens? Now, if you want to change the force here, lever can be used. And if you want to change the voltage, transformer is utilized. So, of course, this is not so much important, but for better understanding, I am giving this thing also. Now, here, one more important point we can observe from this description, that now, what is the technology we have used? Whether it is a mesh analysis or nodal analysis, in order to determine the electrical analysis of the mechanical system in this presentation, which is nothing but the mesh analysis we have used. So, this force voltage analysis, in this force voltage analysis, we can determine the electrical analysis of the mechanical system by using mesh analysis. Now, this also we achieved. One more important remarking point here it is. So, number of mass units in the mechanical system is equal to the number of electrical loops. That is nothing but the number of loops in the electrical system is also same. So, number of mass units in the mechanical system is also equivalent to the number of loops in the electrical system. These two are very, very important points. So, this is the few more points we can write here. The elements of electrical circuits connected in series have same current. Similarly, the mechanical elements have the same velocity, because the current is nothing but this current is analogous to what? Current is analogous to the velocity. So, that made me to write this statement. And each node in the mechanical system corresponds to a closed loop in the electrical system. So, the number of loops equal to the number of nodes. Those are nothing but the masses in the mechanical systems. The mechanical driving force and passive elements connected to the node in a mechanical system should be represented by analogous elements in a closed loop electrical systems. Now, already we know the procedure. and how parameters can be equivalently connected from mechanical to electrical system. Now here, what is the necessity of talking about this analogous systems? Why means, because if electrical, as a being an electrical engineer, if you are talking now, if anything is converted or if the information of any system is available in electrical terminology, people will be more comfortable. So sometimes this information is also required to analyze the given electrical system, because electrical system, sometimes what happens, this may be combined with another mechanical system. In such cases, if you want to analyze or if you want to bring out the complete analysis of the whole system, now we had to convert the mechanical to electrical system. So in that cases, these electrical analogies are very helpful for us. So in order to simplify that electromechanical systems with the help of electrical technology or electrical principles, now this is necessary to derive the electrical analysis parameters of the mechanical systems. And last point is, the elements connected between two nodes in mechanical systems is represented as a common element between two meshes in electrical circuits. Now just you keep this point in mind, and while we are talking about the problems, now we will recollect this point and we will elaborate now what is the exact sense of this particular statement. Now, so far we have assumed that the force is equivalent to the electrical voltage. Now, if the force is equivalent to the current, because in the electrical system there may be two types of electrical inputs. Either voltage might be the input or current might be the input. Now, if the force is equivalent to the current, what is going to happen and what is the procedure to develop electrical analysis, that is nothing but the force current analysis, and how we are achieving the equivalent of the mechanical elements in the electrical systems. So, the last one is electrical analysis, that is the force current analysis. The same we have discussed about the mechanical system. This is the force balance equation is m into d square x of t by dt square plus b into dx of t by dt plus k into x of t is equal to f of t. So this is the second order differential equation, that is the mathematical equivalent of given mechanical system, right? Just go back to the electrical system. Here I have changed that voltage to current, and whenever the current comes into picture, so all the passive elements, that is RLC parameter, can be connected in parallel to each other. So RLC are connected in parallel to the current source. Now I have not disturbed anything because only you can see the mass. And what are the another two parameters, that is the dashpot and spring, those are the properties of the mechanical element. So connecting them in parallel in series doesn't matter here. Only one mechanical system, force only I am going to observe here. I am not talking about any another parameter, because in the mechanical system, if you want to see some displacement, force is the ultimate input available there. So force, let it remain same as the input for the mechanical system. But in the electrical system, we may have two types of inputs. One may be the voltage and one may be the current. About the voltage, if the voltage is the input, and whatever the electrical analysis we have discussed, and here, now from here onwards, let us assume force if it is equal to the current. Then whatever the set of electrical analysis we can develop by assuming force is equal to the current. Now, here, if the current is the input, then RLC will becomes in the parallel. So RLC clearly represented by using the nodal analysis. If you are applying the nodal analysis, what happens here? So this is the input current, and this is the output current, and this is the another output current flowing through the inductor. This is the another output current flowing through the capacitor. Through this resistance, now this is the voltage across the capacitor if it is assumed as the V of t, because this is the response and this is the source, that is the cause. So I of t is nothing but the input, V of t it is assumed as the output. So voltage across the capacitor is nothing but the voltage across the inductor, is nothing but the voltage across the resistor, because these three are parallel. So the voltage across the capacitor, if it is assumed as the output, that will also same as the voltage across the inductor or the voltage across the resistor, because these three are connected in parallel to each other. So current I of t is nothing but the sum of three currents flowing through the resistance, flowing through the inductance, and flowing through the capacitance. Now how much of current it is going to flow through resistance is nothing but V of t by R, because the voltage across this is nothing but the voltage V of t by R is nothing but the current flowing through that. So V of t by R plus current through the inductor is nothing but the 1 by L integration over V of t into dt plus current through the capacitor is nothing but C dV by dt is nothing but the input current. So what is the law we have used here? Kirchhoff current law. Incoming current is also is equivalent to the sum of the currents leaving at that particular junction or node. So now with these two mathematical equations, can we develop any electrical analogy? Can we compare anything here? No, it's not possible because here it is a first order differential equation plus one integrated term is there. So better eliminate the integrated term by replacing this V of t with some suitable parameter. Then let us make an attempt whether it is possible to compare mechanical system and the electrical system. So here you go for the replacing for V of t and let if the V of t can be replaced as d phi by dt. What is this d phi by dt? That is voltage is nothing but the flux linkages, rate of change of flux linkages. Rate of change of flux linkages means n into d phi by dt. So n if it is assumed, number of turns assumed as a 1, then the voltage is nothing but rate of change of flux linkages V of t is equal to d phi by dt. So just use this formula and you substitute here. This is nothing but 1 by R into V of t is nothing but d phi by dt plus C into d by dt of d phi by dt. I am not writing pi of t, just for the simplification I am writing just pi only, plus 1 by L and integration over d phi by dt into dt is equals I of t is the current. So this dt gets cancelled, this d and this integrator cancels, and what happens here? I am writing this second order term first, C into d square pi by dt square plus, and this first term I am writing 1 by R into d phi by dt plus 1 by L into pi is equals current I of t. So this is the equation I am writing here. So this, how I achieved this equation is C into d square pi by dt square plus 1 by R into d phi by dt plus 1 by L into pi of t is equal to I of t. So now you go for comparison between the mechanical second order differential equation and the electrical second order differential equation. So here in this one, right sides are nothing but these are matching to each other. Force is nothing but, if it is assumed force is equal to current, that is nothing but the force current analysis. If the force is equivalent to current, then if you are comparing the second order term, differential one, so in the mechanical system that is M, which is nothing but the equivalent to the capacitance, and first order term is nothing but here this is the conductance is nothing but the reciprocal to the resistance is nothing but the conductance. Here this value is B, and next to spring constant is nothing but this value is nothing but the reciprocal to the inductance. And whatever the inputs, already we have compared the inputs, and what is the output here? Output is nothing but in the electrical system, that output is nothing but the pi of t is the output. Basically, because this second order differential equation is in terms of pi of t only. And here this second order differential equation in the mechanical system is in terms of the displacement x of t. So if the displacement in the mechanical system is equal to the flux passing through the electrical system, then force is also equal to the current, then mass will be equivalent to the capacitance, then dash part is equivalent to the conductance, and spring is nothing but equivalent to the reciprocal to the inductance. So this is this. And next one is coming to the velocity. So this velocity V of t is nothing but the, here this is voltage, because d by dt if you are applying for this expression, so dx by dt is nothing but the velocity is equal to d phi by dt is nothing but the voltage. So here both are V and V, but keenly this is nothing but the sensitively you have to observe the difference between which one is velocity, which one is voltage. And here these are the set of parameters we achieved if the force is assumed to be equivalent to the current in the electrical system. Then this is the set of parameters. Similarly, we have achieved, we have derived if force is equivalent to the voltage, and similarly if the force is equivalent to the current. So these are the two analogy sets available for us in the translational mechanical system. So same thing here, from the previous discussions we can prepare one concluding table Now, if the force is, if it is assumed is equivalent to the current, then whatever the velocity and voltage are same. These are the output parameters, and displacement and the flux will same, and dissipative element B is equivalent to the conductance, and mass will be equivalent to the capacitance, and stiffness of the spring in the mechanical system is equivalent to the inverse of inductance 1 by L, and laws used are Newton's laws as it is in the mechanical, but in the electrical systems, Kirchhoff current law we have used, that is KCL, summation over I is equal to 0, and lever and transformer are same. So, and just concluding remarks, just now also we have observed, and in electrical system, elements in parallel will have the same voltage. Now, what are the elements, how many number of elements connected are connected? If it is in parallel, the voltage across every set will remain same. Similarly, the elements having same force said to be parallel in mechanical system. So, how many number of elements are connected to that? Now, if the force is same, now with the same velocity they will move, and the force is also remain same. The mechanical elements have the same velocity, should have the same voltage in the electrical system, because these two are equivalent to same analogous set parameters if the force is assumed to be equivalent to the current in the electrical system. And one more important thing is, each node in the mechanical system corresponds to a node in the electrical system, and number of nodes are equivalent to the number of masses. So, in the force voltage, number of mass units are equal to the number of loops. In the force current analogy, number of mass units are equal to the number of nodes we had to assume in the electrical system. So, that is very, very important points. With the help of these two simple slides, we can, by seeing the mechanical system itself, we can write down or we can develop the equivalent electrical scheme. So, the mechanical driving force and passive elements connected to the node in the mechanical system should be represented by analogous elements connected to the electrical systems. Now, the last one is also common nodes. It is talking about the common nodes, pair of the nodes. Between the pair of nodes, how the elements can be connected. Let us go back to a simple problem. With the help of that particular problem, this last one could be explained very easily. So, these are the electrical analogies of the mechanical systems, and we have discussed in today's session about the force voltage and the force current analogies, and what is the method, how we are deriving the analysis set of parameters in force voltage and force current separately. I hope you enjoyed this presentation. Thank you very much. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.